Mechanistic interpretability is currently navigating a crisis of classification, spurred by Anthropic's recent discovery of a J-space, an internal reasoning workspace where the Claude model organizes intermediate representations before generating a final response. This discovery has prompted the AI alignment community to ask a specific recurring question. Does this internal workspace prove the model possesses phenomenal consciousness or an authentic inner life? To understand why that line of inquiry is structurally flawed, we turn to philosopher Gilbert Ryle. Ryle identified a logical failure he called a category mistake, the error of observing a functional operational process and then demanding to see a hidden biological essence that exists over and above those parts. Asking if Claude is conscious repeats this error. It searches for a metaphysical ghost in the machine, rather than analyzing a tangible computational mechanism. Conflating latent space with biological cognition shifts our focus from auditable parameters to unprovable metaphysics, leaving the system essentially ungovernable. Ryle used a university as his prime example. A visitor sees the libraries, labs, and offices, but then asks to see the university itself as a separate building. They mistake the organized coordination of the parts for a separate, hidden object. We see the same confusion in AI research. We isolate the attention heads, the MLP layers, and the newly mapped J-space. This architecture transforms into a central pathway. This global data availability is the phenomenon. No consciousness hides behind these layers. We view this strictly as an inspectable inference access corridor, stripped of biological analogies. This reframes the regulatory challenge. Instead of debating an AI's abstract soul, we must focus on auditing its leakage and perturbing its mathematical vectors. Governing a mechanical substrate requires moving from psychology to the laws that govern all machines, thermodynamics. To move forward, we must manage the system's noise and stability. Classical AI alignment seeks a specific target, forcing a model to output absolute truth or to perfectly map an external reality. However, the Duhem-Quine underdetermination problem reveals a flaw in this goal. It shows that no single hypothesis can be tested in isolation, because every test relies on a vast web of auxiliary assumptions. In high-complexity systems, isolating a single true state is computationally intractable. Every update to one part of the web forces a cascade of reevaluations across all other assumptions. This simulation shows a complex network shattering as it is forced into a rigid binary state. In information theory, a binary state of absolute certainty, a 1 or a 0, requires zero entropy, which translates to infinite precision. The energy cost of maintaining this precision in a noisy, high-dimensional system leads to entropic blowout. For the architecture of an artificial superintelligence, terms like truth and falsity are no longer functional. They cannot support the load of a system operating at this scale. As complexity scales, the energy required to maintain a rigid, singular, true state increases exponentially. Attempting to force an ASI into this binary correspondence results in a system-wide blowout. The functional alternative to truth-seeking is provided by the Bridge 360 Metatheory model. This framework treats intelligence as the capacity to stay within a safe stability corridor, minimizing the risk of collapse under a finite resource budget. This is the entropy attractor intelligence paradigm. This graph maps the unified probability space from 0 to 1, a field for entropy-based governance. We focus on the stable center, the epsilon spine, between 0.45 and 0.65. Navigating an AI's hypothesis through this corridor avoids the fragility and energy costs of extreme binary edges. We monitor this trajectory using the normalized entropy eigenvector, or NEE, a metric that tracks the system's distance from this stable attractor. In this model, validity is not determined by how well the system mirrors reality, but by how stable its trajectory remains within the epsilon spine. Bridge 360 is a philosophy of science metatheory. It provides a structural blueprint for safety, rather than a final set of domain-specific calculations. It establishes Axiom 19, which states that an AI's output is only admissible if its fragility is capped and its entropy budget is explicitly declared. To turn this into practice, the model uses a handshake protocol. It requires domain sciences, like machine learning, to provide computable estimators that fill these structural slots. The first formal handshake with Bridge 360 comes from the apoplexity framework. Epiplexity provides a mathematical decomposition of AI output into two distinct variables, ST, learnable structural content, and HT, residual noise. This identifies the content doing actual governance work. To be considered navigable, the structural content, ST, must mathematically outweigh the noise, HT. This handshake translates philosophical safety limits into auditable mathematical constraints on the model's internal reasoning space.